Let's jump right into this explainer and explore one of the most maddening paradoxes in modern medicine. I mean, just think about the human eye for a second. It is literally right there on your face. It is completely accessible. You'd logically think treating it would be as simple as, putting a drop in, right? Well, wrong. Actually, delivering medicine to the correct tissues inside the eye is monumentally difficult. So today, we're going to unpack exactly why this incredibly accessible organ acts like a totally impenetrable biological fortress and how cutting-edge science is engineering microscopic Trojan horses to finally breach those gates. To really grasp the problem, you have to think about the sheer scale we're dealing with here. At any given moment, the normal volume of tears your eye holds is a tiny, tiny 7 to 8 microliters. To put that into perspective, an ordinary single eye drop from a bottle is massive compared to that space. So the moment you tilt your head back and put a drop in, you're essentially trying to park a bus in a compact car spot. Your eye literally just overflows, and a huge portion of that very expensive medication simply spills right down your cheek before it even has a fighting chance to work. And it gets harder because the surface of your eye isn't some passive, still puddle. It is a relentless, highly dynamic defense system. The very second a drug hits your eye, the tear film washes right over it, and blinking immediately redistributes it. And then, every single time you blink, it acts as a mechanical pump. It's actively forcing your medication down the drain, literally pushing it through the puncta into the lacrimal sac and just washing it away. Oh, and if the drug is even slightly irritating, it triggers even more tearing. The eye is actively fighting back against the treatment. So what this means is that your eye is, for all intents and purposes, a biological fortress. Now, its defense mechanisms do an absolutely incredible job of keeping out dust and dangerous pathogens. But unfortunately, your eye doesn't care if it's a piece of dirt or a billion-dollar therapeutic chemical. It just wants it gone. This relentless flushing drastically narrows the window of opportunity for any medicine to actually penetrate into the eye, where it's so desperately needed. Now, let's say a drug somehow miraculously survives that aggressive tear clearance. Well, then it faces a literal chemical and structural minefield, the cornea. The cornea isn't just a simple, transparent piece of glass. It is a complex, multi-stage security system. First up, the drug hits the epithelium, the outer guard. Then it has to slog through the stroma. This part makes up more than 90% of the thickness, and it's densely packed with highly organized collagen. Finally, it has to bypass the endothelium at the very back, which regulates hydration. A drug basically has to possess a near magical ability to successfully interact with all these completely distinct chemical layers just to get a foot in the door. And this is where the physics of it all comes in. And physics is just ruthless. It all comes down to Fick's law of diffusion. Success here requires a perfect mathematical combination. You can't just dump a massive concentration of chemicals onto the eye and hope for the best. Getting inside is entirely dictated by the specific chemical properties of the drug, fighting against the thickness and the complexity of that biological barrier, all while maintaining a high enough concentration gradient to actually force the medicine through. It is a very strict mathematical reality check. Now, you might be thinking, why not just bypass all those walls entirely? Just take a needle and inject it straight into the back of the eye, right? Well, anytime you breach the eye with a needle, you invite a lot of disaster. You're looking at dangerous pressure spikes and the ever-looming threat of devastating internal infections. And when you add in the exhausting reality of patients having to endure these repeated injections over and over again, it becomes incredibly obvious why we desperately need a smarter, much safer way in. So here is where it gets really exciting. This is where we build our microscopic Trojan horse. Nanotechnology completely rewrites the rules of the game here. Instead of just leaving a naked drug molecule to fend for itself against the tear film in the cornea, we can now engineer customized delivery systems called nanocarriers. By wrapping the payload securely inside a microscopic vehicle, we protect it, we dock it exactly where we want it, and we release it over a much more useful, sustained period of time. It's a total game changer. What's truly revolutionary about this, though, is the payload itself. We aren't just talking about your standard chemical antibiotics anymore. These tiny carriers dramatically expand what ocular therapy can actually be. For instance, they can precisely smuggle in genetic material to repair damaged tissues, completely bypassing the need to use viruses. Or they can deliver really powerful agents to fundamentally alter how the eye heals itself, like targeted anti-inflammatories that can suppress the aggressive scarring that so often ruins glaucoma surgeries. But, as you know, any good heist needs a clean getaway. When we talk about sustained delivery inside the eye, there is a massive divide in how we do it.
You can absolutely use non-biodegradable implants to deliver drugs, but those remain permanently physically present inside the eye. Some of them even require surgical suturing. In stark contrast, a biodegradable nanocarrier does its therapeutic job for months, and then it simply vanishes. It breaks down entirely safely. You get the payload delivered, and you don't leave a permanent piece of foreign hardware sitting behind in one of the most delicate organs in your entire body.
We do have to be incredibly careful, though, because that disappearance has to happen exactly on schedule. More time isn't always better. Take corticosteroids, for example. They offer fantastic anti-inflammatory benefits. But if a nanocarrier leaves them active in the eye for too long, you are suddenly facing massive spikes in intraocular pressure and rapid cataract formation. The vehicle and the drug are an intricately linked system. The timing of the release and the degradation of the carrier have to be flawlessly calibrated to the delicate ecosystem of the eye.
So when you put this all together, the obstacle course is frankly staggering. A sophisticated delivery mechanism is pretty much useless unless it achieves a perfect, multifaceted balance. It has to survive that rapid tear clearance, it's got to penetrate those highly complex layers of the cornea, it needs to reach the deep tissues without causing invasive harm, and above all else, it has to do it all with absolute, crystal clear biocompatibility. It must cause zero toxicity or inflammation that could disrupt the patient's normal vision.
As we wrap up this explainer, we are left staring down the ultimate therapeutic puzzle. Realistically, there will probably never be one single, universal magic bullet for the eye. The grand challenge we are facing now is hyper-customization. I mean, how long until we can engineer nanocarriers that don't just passively deliver a drug, but actively adapt in real time to the eye's ever-changing chemistry, to deliver exactly the right agent to precisely the right site for the perfect amount of time with zero toxicity? The biological fortress is finally starting to crack, but the race to completely conquer it, that is really just beginning.